All right, onward into chapter 4, which is a little bit of something different than what we've been doing. Chapter 2 and 3 were about what we call kinematics. Kinematics means the mathematical language we use to describe motion, and in particular, we spent some time describing constant acceleration motion, but there are other kinds of motion where the acceleration isn't constant. That just happens to be one that we're focusing on a little bit more in this course. In contrast, chapter 4 is about dynamics, and dynamics means analyzing the forces and how they cause subsequent motion of an object. So once you analyze the forces, then you can use your kinematics to describe the motion. All right, so we've been using our intuitive notion of forces, and now we're going to make it a little bit more explicit by, as we go through this chapter, describing different kinds of forces and getting familiar with how they act, and also knowing how they relate to our dynamical quantities, how they relate to acceleration. So a force is always an interaction between two objects. That means if I take my finger and push down on the table, my finger is exerting a force on the table, but I can't do it in such a way that the table doesn't exert a force on me. I can feel it, right? I'm pushing on the table. I feel the table pushing back on me. If I pull on a door handle, the door handle's pulling on me as well. So it's always an interaction between two objects that are exerting forces on each other. Some forces, like the finger force on the table, is what we would call a contact force. It means two objects are touching and pushing because they're touching each other. But other forces, in particular gravity, are called action at a distance forces. So the Earth pulls on the moon even though it's not touching it in the normal intuitive sense. So we're going to use both of them. We'll describe gravity. We'll describe contact forces quite a bit too. We're going to describe each force exerted on an object by a vector, and usually an object will have forces being exerted on it from various other objects that it's in interactions with. So for example, an object sitting on a table has the Earth pulling down on it with gravity, and then the table's pushing up on it with a different force. So we'll describe those forces by vectors because they have a strength, the magnitude of the force, and a direction in which the force is being exerted. The term net force, or I can't remember if Giancarlo uses the word resultant, some books do that too. The net force on an object means you add together all of the forces that are acting on an object. Now each force is a vector, so when we say add together, we mean addition in the sense of vectors. So if an object has, we talked about how to add two vectors before, you can add four vectors sort of one or two at a time. So if an object has four vectors being exerted on it, four forces, we can add the first two and get the sum of those two, and then take that vector, add it to the third, just adding those two vectors, and then take that result and add it to the fourth. So we know how to add lots of forces together. We can just do them two at a time and get the sum of all of them. So that's the net force. In order to analyze how the net force is going to affect the motion of the object, we're going to draw a little picture called a free body diagram. So if we're concerned about a particular object, we're going to draw a diagram that shows all of the forces acting on the object as labeled arrows, right? Each force is a vector, and we want to show the directions they're pointing in as they act on the object at a particular moment in time. So just as an example of a free body diagram, I don't use acronyms too much, but sometimes we write free body diagram takes a little bit of effort to write down, so I'll just write FBD. There are a few acronyms that I'll use, but not too many. Here's a person sliding a heavy box on a floor, pushing it along maybe at a constant speed, right? So if we're concerned with the box, that's the object we're concerned with, suppose. The person is pushing to the right on the box, but friction, the person is also having to overcome some friction from the sliding of the box on the floor. So the floor is pushing by a friction force to the left in that case. So those are two of not all the forces acting on the box, but if we were to draw a free body diagram for that box, we could draw four forces acting on it. First of all, there's the applied force, and it's acting to the right. And notice that when we draw free body diagrams, even though the person is pushing on the left-hand side of the box over here, we always draw forces that are acting on the box so that their tails are attached to the object that we're drawing the free body diagram for. So even though the person is pushing from the left, it looks like I'm drawing a force where someone's pulling from the right, but there's not going to be any distinction in terms of how they affect the motion of the object. So we'll always draw them with their tails on there rather than the arrowhead being on the object if we drew it on this side. So there's an applied force, there's a friction force going back. Gravity, of course, the Earth is pulling down on the box, and we'll talk about that force quite a bit later on. But we know that gravity is trying to pull the box down towards Earth, and the floor is getting in the way, so there's a gravitational force in the downward direction. And then, if there weren't any other vertical force, the box would start moving downward. And we'll describe how that works in detail later on, but we need an opposing force to keep the box from going through the floor. That's the floor pushing up on it, and sometimes we call that a normal force. Normal just means perpendicular to a surface. So relative to the surface the box is sliding on, the normal direction is exactly straight up from the Earth if this is a piece of flat floor. And so we got a normal force going up. We'll learn more about these forces as we go on, but for right now we're just sort of qualitatively drawing them in a diagram. Similarly, here's a coffee mug sitting on a horizontal table. If I drew the free body diagram for the coffee mug, there really are only two forces on it. In other words, we don't really need friction to act on the coffee mug because it's perfectly happy to sit still even if there's almost no friction on the table, assuming it's a perfectly flat table. So we've got a gravitational force going down, a normal force going up. No one's pushing from the side, and it doesn't seem like there's much of a friction force that's necessary here either. So we're going to use those free body diagrams. We'll see how they come in later on. Now we're going to describe the famous Newton's laws of motion that tell us how to turn those free body diagrams into some sort of relationship that will allow us to determine the acceleration of the object. So we'll take them one at a time. First, Newton's first law. The first law is about the ways in which we can view some sort of events, like balls colliding, or in here, the event is just the fact that this ball is sitting here. Okay, so here's a red ball. I'm imagining it's in outer space, and here's a little space pod that's sitting at rest with respect to the ball. And there's lots of different ways we could observe the ball. One way we could observe it in this particular case is just by sitting right in front of it and looking out the window at the ball, and we can make measurements. And someone might in there might say, look, the ball is sitting, it has zero velocity, it has zero acceleration. But there are other points of view that might disagree with it. For example, consider another observer looking at the ball. We'll call that observer B, and that observer is floating along in a spaceship, and they look out their window and they look at the ball. That spaceship, at least from the point of view of the picture I'm showing, is moving to the right. When they look out the window, they're going to see the ball. The spaceship was moving to the left. When they look out the window, the ball will appear to be moving to the right, and it actually will be moving to the right. So that second observer B is going to say, the ball has a non-zero velocity. It's moving to the right with a certain speed, according to me. It's not even that simple. Consider observer C, who starts out at rest with respect to the ball, but then fires some engines and observes the ball as they start zooming off to the right. So observer C would say, well, initially the ball had zero velocity, but then its velocity got bigger and bigger and bigger to the right. In other words, I saw that ball accelerating from my point of view. Okay? And this is all very confusing. It seems like, well, depending on how you observe something, you could make it seem like it's moving however we want. And so Newton's first law is a way of simplifying all this down and saying, we're not going to allow all these different points of view. We'll allow some of them, but we're going to restrict it a little bit. Okay? Newton's first law says you can always find a perspective, and not all perspectives are going to be like this, but we can always find a point of view from which to view an object or an event in which every object that doesn't have any forces on it, or at least the forces cancel, so there's no net force on it. The net force is zero. If there's no net forces on it, it moves with constant velocity. So if I'm looking at an object, one of the first things, if I want to know that I'm looking at it from this point of view, one of the first things I need to do is look at it and decide, are there any forces on it? So that ball, if it's just sitting there hovering in outer space, we might say, well, it's far from large gravitational objects, so it seems like there's no gravitational forces on it. Nothing's touching it, so there's no contact forces. I don't see any charged electric objects, so there aren't any electric forces. Looks like there's no forces on it. So I ask myself the question, if there's zero net forces on it, does it move with constant velocity? And if so, then that's some evidence that I'm viewing it from the point of view of an inertial reference frame. And that's what we're going to call this kind of viewpoint. A viewpoint from which every object with zero net force on it. When you add all the forces, they either cancel out or there's no forces, then there's nothing to cancel. It's just zero force on it. If there's no net force on it, it moves with constant velocity, and that's true for every object. We'll call such a viewpoint an inertial reference frame. And we're always going to choose inertial reference frames in order to analyze motion for the rest of the course. We'll do a couple of examples where we look at points of view from non-inertial reference frame, but generally we're going to try to choose inertial reference frames. And that means back in this example here, observer A, assuming this ball doesn't have any forces on it, observer A would comprise an inertial reference frame. Observer B looks out the window and says, no, I don't see any forces on the ball, and the ball is moving with constant velocity to my right. So observer B is also an inertial reference frame, and it doesn't really matter which one you use, although, observer A might make the analysis a little bit simpler because the velocity is actually zero. Observer C, they look out the window and say, nope, no forces on the ball, but the ball is starting to accelerate to the right. That is telling me if there's no forces on an object, but I see that object accelerating, it should be moving with constant velocity if I'm in an inertial reference frame. So I'm going to conclude that I am not observing from an inertial reference frame. Don't do that in this course. We're going to specialize to only analyzing things from inertial reference frame points of view. All right, let's practice with this a little bit in a voting question. We're imagining we're looking at something from the point of view of an inertial reference frame. So don't worry too much about how we know that, but when we're watching this car move right here, we're watching it from an inertial reference frame, and it's rounding a circular curve while maintaining a constant speed. So it's going around the curve at a constant speed. It's not speeding up or slowing down, but it is changing its direction. The question is there a net force on the car as it rounds the curve? No, yes, or it kind of depends on the details of what's going on there. So take a moment and think about your answer. The correct answer here is yes. If we're guaranteed that we're looking at this car from an inertial reference frame, its velocity is not constant. In other words, its velocity vector first pointed this way, then this way, then this way, so its velocity is changing. And therefore, if we're looking at it from a point of view of an inertial reference frame, the only way for the velocity vector to change, in other words, to not move with constant velocity, is for there to be a net force being exerted on the car. So that means when we add all the forces that are acting on it, they can't add to zero in this case because it's not moving with constant velocity. We know we're looking from an inertial reference frame. Now, the question we want to get to, or answering, which is going to allow us to calculate things, is when we view some events from an inertial reference frame, how do the forces on an object affect the motion of that object? And the answer we're going to give very shortly, but it depends on the concept of the mass of the object. The mass is going to come into the equation we use. And we all have some intuition about mass, but it's important to be a little bit more precise in physics. In particular, what's the difference between the mass of an object and the weight of an object? Mass is a measure of the resistance to the change of the state of motion of an object. In other words, when we say the state of motion, we mean moving with a certain velocity. And if we change its velocity, we're changing the state of motion of that object. So the harder it is, you can imagine being in outer space, and I could say, here's a little ping pong ball, and here's a huge asteroid. If the ping pong ball and the asteroid are coming by with the same speed, how easy is it for me to change the state of motion of the ping pong ball? Oh, it's easy. I just give it a flick with my finger and I can cause it to shoot off in a different direction. That means that the ping pong ball has very low mass. Low mass objects are very easy to change the state of motion. Whereas if I flick the asteroid with my finger, it's going to be very painful and I won't see any appreciable change in the motion of that asteroid. You know, same thing's true if a little ball comes by versus a bowling ball and I kick them with my foot. It's very hard to change the state of motion of a bowling ball compared to a little ping pong ball. So sometimes people use the word inertia. Inertia means exactly the same thing as mass. Inertia means how hard is it to get something moving, or once it's moving, how hard is it to change how it's moving. That's a measure of the mass. Mass is not the same thing as weight. Weight is a gravitational force on an object, whereas a mass is a measure of how hard it is to get it moving. And we can see that they're different in that weight is, intuitively how heavy an object is. So if I have a bowling ball and I'm holding it in my hand, it's very heavy. I would say it's definitely got a pretty hefty weight, and it also has a pretty big mass because it's hard to change its state of motion. But to see they're not the same thing, imagine moving that bowling ball out to deep space. In deep space, it's just as hard to change the state of motion of the bowling ball, so we would say it has the same mass in deep space, but we would say its weight is 0 out there. In other words, if I put that bowling ball adjacent to a scale, it's not going to push on the scale at all. In fact, if it did push on the scale, it would cause the scale to shoot away from it. So if I put that bowling ball next to a scale, the scale's going to read 0 force, and therefore the two are different. Weight depends on how close you are to a large mass object that's exerting a gravitational force on you, whereas your mass is the same no matter where you are in the universe. So the reason they're confused often is because the two are proportional on the Earth's surface. The more massive an object is, the more its weight is on the surface of the Earth. But if I put that bowling ball on a scale on the surface of the Earth, and then I put the same bowling ball on a scale on the surface of the moon, it's not going to read the same value on the scale. The scale is reading the weight, and we calibrate them to read the mass on a scale, but that's only because we're assuming they're always going to be used at the surface of the Earth. They wouldn't be correct anywhere else. So we often measure the mass of an object by measuring its weight because we're assuming we're doing it here at the surface of the Earth. So imagine you're an astronaut in outer space, far from any heavy objects, and you find a little rock floating by and you want to know what the mass of the rock is. Maybe it's hollow and it's almost, filled with porous kinds of things, so there's hardly any mass at all. Or maybe it's a really heavy chunk of iron, but you can't tell visually. How would you determine whether it's a really massive object or a really not so massive object, a light object, if you will? The way you can do it is by trying to change the state of motion of the object. So you could have it fly by and flick it with your finger, or even more simply, you could take that object in your hand and shake it back and forth. And the harder it is to shake it back and forth, the more massive the object is. It doesn't depend on the weight, it only depends on the mass. We're trying to change the state of motion of the object and seeing how difficult it is. Okay. Now that we know a little bit about mass is just how much, how hard it is. It's the same as inertia, how hard it is to change the state of an object, state of motion of an object. We can state Newton's second law, which is really going to be important for us because it tells us how forces cause motion. When an object is viewed from an inertial reference frame, so we're only going to specialize to that case, the net force on an object is equal to the object's mass times the resulting acceleration of the object. So when we add all the forces together, they determine the acceleration. And if we know the acceleration, maybe we can figure out where it is as a function of time. For example, if the net force is constant, then the acceleration will be constant as a function of time, and maybe we can use kinematics, those kinematics equations from last chapter. This is true at every moment in time, no matter what. So the forces may be changing, and at every instant, the net force might be a little bit different, and that means the acceleration is going to be a little bit different. But that equation holds at every moment in time. Now, what about the SI units for force? We've talked about SI units for mass. Well, I guess we haven't talked about it. We should talk about it now. SI unit for mass is in kilograms. So the harder it is to change the state of motion of an object, the larger its mass is, and it's measured in kilograms. The acceleration is measured in SI units of meters per second squared. In other words, we defined it as a change in velocity, which would be in SI units of meters per second, divided by a change in time, which puts an additional second factor in the denominator. So the SI units for acceleration are meters per second squared. And so if we put those together, the SI units for force would be kilogram times meters per second squared. We know when we write down any equation in this course, it's dimensionally balanced. So if we put in SI units on this side, we're going to get the same SI units out on this side. So the SI units for this side are kilogram meters per second squared. But we talk about forces so much, we're going to define a kilogram meter per second squared as a Newton. And that's the simplified unit given by the symbol capital N. So we'll measure forces in newtons, but they can be expressed in terms of mass and distance and time. So they can be expressed in terms of those three fundamental units, but oftentimes we'll just write newtons because we want to be brief. All right, here's another voting question. You're a passenger in a car not wearing your seatbelt. You think about this from the point of view of the passenger. You've all experienced this. Without increasing or decreasing the car's speed, the car makes a sharp left turn. You're in the passenger seat, and unfortunately you're not wearing your seatbelt. And if someone turns to the left really quickly without slowing down, you're going to slam into the passenger side door. Okay, so you find yourself colliding with the right-hand door. Which of these is a correct analysis from the point of view of Newton's second law? A. While you're moving toward the door, and after you collide with the door, there's a rightward force pushing you into the door, right? I start moving toward the door, so there's got to be a rightward force pushing me into the door. And then it continues to push me into the door as I feel my shoulder mashed into the door. B. Starting only at the time of the collision, the door exerts a leftward force on you. Or C, some combination of the two above are correct, or D, neither of those statements is correct. Oftentimes this question stirs up a little bit of controversy in class, and it's an important voting question, not necessarily an obvious one from the beginning, but we're going to take the point of view of someone kind of floating above the car and looking down and watching as the car is going by, and we'll see that B is the correct answer. Even though I think I see myself being pulled toward the door, there's no force pushing me toward the door, as is stated in A. There's no force pushing me at all in the horizontal direction until I hit the door, and then it pushes on me. Imagine someone floating above as the car is driving by underneath, and at this instant the car suddenly starts making that left turn and turning like that. Now, if this is the point of view of an inertial reference frame, there's no reason to think not that if I'm just floating above a car like this, it should be an inertial reference frame. I am moving along happily at constant velocity, and given that I don't have any forces on me in the direction, the horizontal direction, it seems like I would like to keep going along that line. That's what Newton's first law says. If there's no forces on you, you would like to keep going in a straight line. And I do try to keep going in a straight line until that pesky car turned and slammed me in the shoulder. I would have kept going in this direction until the car turned around and slammed into my right shoulder and exerted a leftward force on me. So this is the point of view that Newton would take from this car. We're observing it from the point of view of an inertial reference frame, and there are no forces on me that push me into the door. Rather, if there were such a force, we would have to describe, well, what is it that's exerting that force that's pulling me into the door? It's not a gravitational force between me and the door. So this is the point of view that Newton would take from the point of view of an inertial reference frame. There's no force on me until I slam into the door. Of course, there are the gravitational force and the force upward from the seat are on me, but there's no forces in the horizontal direction until I slam into the door, and then the door is exerting a force on me. I can feel it at that point. All right, one last thing and then we'll stop. This is kind of a long video compared to some of the other ones. Here, when the space shuttle is in orbit, things inside are weightless. And what that means is if you drop any object in front of you, it doesn't drop at all, it just floats there. For example, if you let go of a hammer, the hammer's going to float right in front of you. And yet, if I pull back and look from the point of view of someone, looking, just sitting at rest above the Earth a large distance away, there's got to be a significant gravitational force acting on the shuttle and on the hammer because Earth keeps the shuttle moving in a circular orbit. If there weren't a force on the hammer would keep going straight. But look, I'm watching it from this point of view of someone who's pulled back way above the Earth, and the hammer's going in a large circle. It's not going in a straight line. So there's got to be a force on it. The only force available is the gravitational force that's causing it to move in a circle. So back to the point of view of the person inside this space shuttle, why doesn't the hammer accelerate? And the answer is, well, it depends on which point of view you're taking. The point of view of the person inside, the point of view of the person watching from far away from the Earth, watching this thing go around the Earth, is an inertial reference frame point of view. We see there's a force on the hammer, and the result of it is the hammer doesn't go in a straight line. That's just Newton's first law, sort of the reverse of Newton's first law. Whereas the point of view of the person inside the space shuttle is a point of view of a non-inertial reference frame. It's not an IRF. And that means we can have things that have net forces on them. We look out the window and we say, look, the Earth's over there. There should be a huge force on this hammer, but it's not accelerating. If you see a net force on an object, but it doesn't accelerate, or if you see no net force on an object, and the object does accelerate, that's a sign that you're viewing things from a non-inertial reference frame. So this space shuttle point of view is confusing because we're viewing things from a non-inertial reference frame point of view. It's the same with this voting question. The point of view of the passenger, once the passenger starts to accelerate around the corner like that, they are in a non-inertial reference frame, and therefore they might see, oh, look, I feel a force on my shoulder, and yet I'm not accelerating because I'm just sitting here at rest in the car. Well, that's true from their point of view, but that's not the point of view of an inertial reference frame. So we shouldn't expect Newton's second law to be true in those cases. All right, long video, but let's take a break and then go on and start into the description of some forces.